Let's use calculus to solve a minimization problem. Sometimes it's called an optimization problem. This is a very old one that was first solved by Heron of Alexandria in the Roman era. So the idea is, as a story, you have some young man, that lives in a newer village over here, a distance A from a river. This is a river. And his mother lives in the next town over in an old village, a distance B from the river. And every morning the son has to walk to the river, collect water, and then bring it to his mother. So he wants to minimize his walking path to the river and then to his mother. He walks following two straight lines. So the optimization here is to find the point along the river that minimizes his walking path. If he walked straight to the river and then straight to his mother, that would be a longer path. So he wants to walk somewhere between his village and his mother's village. Okay, so the parameters of the problem is that the boy's village is a distance A to the river, and his mother's village is a distance B to the river, and the length of the river between the two villages is a distance capital L. So we want to find this point. So we introduce then our unknown into this problem. We'll call it x. So we'll call x here to be the distance from the perpendicular of the boy's village to the point that he collects the water here. And then because the total distance is L, then this distance here becomes L minus x. We want to minimize the distance of the these straight lines that go from the village to the river. Those are just the hypotenuses of two right triangles. This one is the hypotenuse of this triangle. So this distance here would be the square root of x squared plus a squared. This distance here is the hypotenuse of this right triangle with sides b and L minus x. So this would be the square root of L minus x squared plus b squared. So we want to minimize then the distance that the boy walks. So that distance I can call d is going to be the sum of those two distances. So x squared plus a squared square root plus the square root of L minus x squared plus b squared. So capital D is the distance the boy walks, and we want to find a minimum of d with respect to x, and that will give us the position on the river that the boy should walk to, which is right here. Okay. So how do we find the minimum of a function? We take its derivative and we set it equal to 0. So we're looking then to take the derivative of capital D with respect to the variable x. So how do we take the derivative of this function? We're taking the derivative of these two terms. So if we look at the derivative of this first term here, we have, this is a power law, x squared plus a squared to the 1/2 power. We use the power rule to take the derivative. So it becomes 1/2 x squared plus a squared to the negative 1/2 power. And then we need to use the chain rule and take the derivative of the inside, which will be 2x. So if we put that together, if it's hard for you to see that in your head, you can stop the video and try to do it on paper. But I think I can do this in my head. The 1/2 will cancel the 2, so we'll end up with an x divided by the square root of x squared plus a squared. So that's from the first term. Then we take the derivative of the second term. It's the same idea. We have L minus x squared plus b squared raised to the 1/2 power. We take the derivative, so we have a 1/2. And then we have L minus x squared plus b squared to the negative 1/2 power. That puts the square root in the denominator. Then we have the derivative of the inside, which is 2 times L minus x. So the 2 will cancel the 1/2. And then we have the derivative of L minus x, which is the inside of the inside. And that will be a negative 1. Okay, so we have a double application of the chain rule here. And that gives us a minus sign. And then we have an L minus x in the numerator. And then in the denominator, we have an L minus x squared plus b squared. Again, as a beginning student in calculus, this would be too much for you to do in your head. So if you need to, you stop the video, you get a piece of paper, and you show that this term here is the derivative of this second term. Okay, we're solving a minimization problem. We're finding the minimum of the function d with respect to x. So we want this to be equal to 0. That gives us an equation. So we have x over the square root of x squared plus a squared is equal to L minus x over the square root of L minus x squared plus b squared. Okay, and that's our equation for x. So there's an easier way to write this equation. If we look at what is x over square root of x squared plus a squared, we look at this first triangle here. That's this side x divided by this hypotenuse. So if we put an angle here, let's call it theta 1, then the cosine of this angle, theta 1, is the adjacent x divided by square root of x squared plus a squared. So that's just the cosine of the angle theta 1. Likewise, this other term, the second term on the right-hand side, is this side of the triangle, L minus x, divided by the hypotenuse, L minus x squared plus b squared, square root. That's the cosine adjacent over hypotenuse of this angle. So this angle I can call theta 2. So this is equal to the cosine of theta 2. Both theta 1 and theta 2 are between 0 and pi. So that means these angles have to be equal. So what we've found was that the path that minimizes this distance, the shortest path, is the one that makes these two angles, theta 1 and theta 2, equal. Let me summarize. This is an old problem, but a very interesting application of the calculus. It's called the shortest path problem. It's a minimization problem. We find a distance with respect to one variable. Here I call it x. And then we minimize the distance by taking the derivative of capital D with respect to x and set it equal to 0. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.